This section is about inverse functions. So when working with functions, you may be asked to not only determine whether the function has an inverse or not, but also graph the inverse of the function and the actual function, the function and its inverse in the same coordinate system. And you may want to know the characteristics on a coordinate system to know whether the two functions are inverses by only looking at the graph on the coordinate system. But not all functions have an inverse. So we need to see to know why and determine the conditions on a function in order to be qualified to have an inverse. So first, let's look at one-to-one function. A one-to-one function is a function. First, it needs to be a function. Need to be a function, meaning that you're looking at the graph of such function. Needing to be a function, it needs to pass the vertical line test. I say you have a relation, you have a graph, right? To know that this graph is the graph of a function, you need to be able to draw vertical lines, and all the vertical lines should intersect this graph only once. Under this condition, all of them, if all of the line cross this the graph of the function only once, you know that the graph of this relation, not the function yet, because it needs to pass the vertical line test to be a function. It's a relation until passing the vertical line test. Now, if you want to have a one-to-one function, not only that you want this graph to pass the vertical line test, but you want it to pass the horizontal line test. Like the first one, it passes the vertical line test, but also passes the horizontal line test, meaning that all horizontal lines will cross the graph only once. All vertical lines will cross this graph only once as well. So this is a one-to-one function. Well, I'm looking at this one here. It is a function, right? Passes the vertical line test. Unfortunately, it will fail the horizontal line test, right? You see this, which makes it not a one-to-one function. It's a function, but not one-to-one. Now, if it's not one-to-one, it does not have an inverse. Because when the inverse exists, it should be unique. So we're looking at the blue line. This line here. It is a one-to-one function because it passes the horizontal, and then you expect all the lines, vertical or horizontal, to intersect this only once. It is one-to-one. Now you're looking at the fact that it has a one-to-one function. It does have an inverse. The inverse would be this one here. Now what I want you to see here is the symmetry between the function and its one-to-one. So say we take this point here. We take this point of the graph. I'm trying to take specific point. If I take this point here. This point is separate from this line y equals x at the same distance to the same point on the other side on the symmetry. So what I'm trying to show you here is that the function and its inverse are symmetric about the line y equals x, or f of x equals x. They are symmetric. And then if they have to meet, they will meet on this line, y equals x. Every time that they're meeting, they are expected to meet on the line y equals x. They may not meet, but if they have to meet, then they have to be meeting on the line y equals x. So that's the principle. First, you need to have a function that is one-to-one. That means each x has exactly one y and each y has exactly one x. That's one-to-one. And if it's one-to-one, it has an inverse. So one-to-one functions have an inverse. And then moreover, the graph of two one-to-one functions, the graphs of two one-to-one functions are symmetric with respect to the line y equals x. Graphs of two inverse functions are symmetric with respect to y equals x and meet or intersect on this line. This line. They intersect on this line as well. So basically, that's a sign for you to identify the graph of two inverse functions. So one-to-one functions have inverse, and the graph of two inverse functions are symmetric with respect to the line y equals x and intersect on this line if they have to intersect. Sometimes they don't intersect. Another thing that I want you to see before we start doing some examples, let me take the example of a parabola function. So I take this parabola. Obviously, the parabola is not one-to-one. A quadratic function is not one-to-one. The reason is it doesn't pass the horizontal line test. Now, if you want it to be one-to-one, you can just remove one side. Well, that's the function f of x. F of x equals x squared for all real numbers. For all real numbers, it's not going to be one-to-one. Thus, did not have, doesn't have a, thus it doesn't have an does not have an inverse. Well, for it to have an inverse, we can remove one side. It will be 1-to-1. Oops. It will be 1-to-1. If we remove one side, now it's 1-to-1. Because this part of it, which is the same function, obviously the same function, but taken from this to positive infinity, from 0 to positive infinity. So that means for x greater than or equal to 0, it's going to be 1-to-1. So part of it, half of it can be 1-to-1. And then the inverse would be the function that is symmetric with respect to the line y equals x. The line y equals x would be this line. Symmetric to this would be a graph like this one. Now, it's not going to be perfect. It's something like this, which would be radical of x, positive. So a 1-to-1 function, a function that's not 1-to-1, you can take it into some restricted interval to bring it to a 1-to-1 function and think about how you would find its inverse. So that's the purpose of this part of the lecture, is to, one, telling you that not all functions are 1-to-1, and telling you when not all functions have an inverse, and show you when a function has an inverse or not. And having an inverse means that the function is 1-to-1. The function is 1-to-1 when each x has exactly one y, and each y has exactly one x. Each input has exactly one output, and each output has exactly one input. So if you fall in a case where you have a function that a relation that is not 1-to-1, then this function will not have an inverse unless you restrict it into a certain interval. So let's look at some examples here. I have this graph, right? I have the graph of this function here that is obviously that's a portion of a polynomial function. If you want to see that, it could be that part here. Oh, that's not perfect, but I'm trying to get it as perfect as possible. Well, that would have been the other part of the function, but it's taken off, because if it was like that, then you would not be able to say that this is a 1-to-1 function. It doesn't pass the horizontal line test. Then after that, if you remove this, then you get a 1-to-1 function that will pass both vertical and horizontal line tests. So yes, this function is 1-to-1. Obviously, that's this graph here, because you see how it intersect. It's this, the x equals -5. So that would be for y equals 0, x would be -4 for y equals 0. So yes, that's this graph, but we only take it on one side of the graph, or we don't use the other side, so that we can keep this function 1-to-1. So now in this case, we will show you the steps taken when you're looking for the inverse of a function. So first you need to identify whether the function is one-to-one or not. And then after you get you know that this function is one-to-one, you can take steps to finding its inverse. If it's not one-to-one, you don't need to do any work that would lead to finding the inverse, because one-to-one functions only have inverse. Now, let's look at the steps to find the inverse. Step one, we substitute the f of x equals, or g of x equals, or any letter of x equals by y equals. So that's your step one. You want to write it as y equals whatever the expression was. The next step is to swap the x and the y. You want to have x play the role of y into this equation. Next, you solve the new equation after you swap x and y for y. You isolate the y. And then last, after you get y by itself, you replace y by f inverse of x. That's not f exponent -1, but that's f inverse. F inverse of x. And then once you do that, you get your inverse, the inverse of your function. Now let's go ahead and do this. Step one, we replace f of x by y. So that's y equals x plus 5 squared minus 1. Next step, we exchange x and y. So that's x equals y plus 5 squared minus 1. Step 3, we're going to solve for y, get y by itself. So that's plus 1 on both sides. So x plus 1 equals y plus 5 squared. We're not going to forget that they only use one side. That's why we had from negative x, from negative 5 to 1 to infinity, from negative 5 to infinity, which makes this always a positive or equal 0. So if I take the square root of it, it will be positive. I don't need to take plus or minus because this is always positive. So the square root of both sides, we don't need to use plus or minus because it's always going to be plus. Since this is positive, x plus 1 equals square root of x y plus 5 squared. Square root of something squared, if the thing is positive, would be the thing. So that's y plus 5 equals the square root of x plus 1. And then we can subtract 5 on both sides. Y equals the square root of x plus 1 minus 5. We got y by itself. Now we can write the f inverse of x. The inverse of the function is the square root of x plus 1 minus 5. So that's the function. And the other thing that I did not mention earlier is that inverse functions, they exchange domain and range. So if f is a function from domain of f to the range of f, domain and range, f inverse will be from range of f to domain of f. You just swap just like when you swap x and y, and then the domain of f of x is the range of f inverse, and the range of f of x is the domain of f inverse. So that's why we've already known what the domain of f was. And if you look at the graph, you will see that it starts from -5 and it goes all the way to infinity. So we know the domain of f was -5 to positive infinity, which will also be the range of f inverse, -5 to infinity. Now we need to find the domain of f inverse that will be also the range of f. Well, this is a radical function. We remember from the last module, the last topic, to find the domain of a function that has a radical, you need to have the expression inside of the radical to be positive. Otherwise, you won't be able to solve it. You won't be able to see any, you won't be able to solve a radical if the expression inside is not positive, or you are doing the work in a set of complex numbers. We're only doing these functions in the set of real numbers. If something is not real, that means it doesn't exist in the real numbers. So domain, we're going to look for domain of f inverse. We need to have x plus 1 greater or equal 0. That's the only way f inverse will exist, because square root of x plus 1 exists only if the expression inside is positive or equal 0. We would subtract 1 on both sides. X is greater or equal to -1, which means the domain of f inverse is from -1 to infinity. So that's from -1 to infinity, which is the same as the range of f from -1 to infinity. Let's see another example. Well, also, we are asked to graph the inverse of the function. Well, the first thing I want to do is I want to sketch the line f of x equals x. F of x equals x. And then we know that the symmetry would be the inverse of f of x would be symmetric to this line. So that means I will have a point here that will be the symmetry of this one. You can also use your graphing calculator to find points, which will be also okay. And then I also see this point here that I can find its symmetry. As long as I can find 2 points, I'll be fine. Trying to find its symmetry here, because that is 3, -3. So I would go, so that'd be this. X equals -3, y equals +3. Then I would go y equals -3, just swap x and y. So to get a point for the inverse, and then I need another one. Let me take this one here. That's 8, -2, 8. So 2, -8. -2, 8. So 8, -2 would be the inverse. Okay, and then I can just sketch this. That is the graph of F inverse. And then that's F. Here's our next example here. In this next example, it's easier because we need to make sure that the function is one-to-one. Well, this function is a line. We can graph it first to see whether it's one-to-one or not. We know if it's one-to-one, it would pass both vertical and horizontal line test. So we're gonna graph this line. The y-intercept is 8, x equals 8. The slope is -4. That means down 4. 1, 2, 3, 4. And then over 1. If we want to connect these dots to create the line. So we're going to have that. And then okay, so that's a graph of f of x. That's f. Obviously, one-to-one. So because it's one-to-one, we can go ahead and find its inverse. But before I go, let me just sketch the line f of x that y equals x, because I'm gonna need it. So y equals x. And now let me find the inverse. Step one is set y equals -4x plus 8. Swap x and y. So x equals -4y plus 8. Subtract 8 on both sides. So we got x minus 8 equals -4y. Divide by -4. So we have y equals -1/4 x plus 8/4 is 2. So for this one, we can sketch this line. I'm going to, instead of sketching this line, I'm going to find points of the inverse, 2 points of the f of x, and then sketch this, then verify it with the slope of the line. So this point here is x equals 1, y equals 4. So I'm going to look for 4, 1. X equals 4, y equals 1. So that's x equals 4, y equals 1. 1. X equals 4, y equals 1. So that would be the symmetry for that one. Now I'm going to need a symmetry for this one. This is 0, x equals 8. X equals 0, y equals 8. So x equals 0, y equals 8. I'm going to need y equals 8, 0, x equals 8. We swap them. See, same distance. Now I can connect these two lines, these two dots to create the line. And I expect them to meet. If they meet outside of they should meet on the y equals x line. That's f inverse. But if you go use the slope and the y-intercept, well, obviously I didn't finish that. That's f inverse of x equals negative 1 over 4x plus 2. So that's 1 over 4, negative 1 over 4x plus 2. So you would see this mean that's the slope, that's a y-intercept, and the slope was negative 1 over 4. So that's down 1 and over 4. See, that would give you the same line. But I prefer using the inverse to sketch it so I can make sure that it's symmetric with the line y equals x. On our next example, it's the same process. It's the same process. So we want to sketch a graph and then find out what the inverse is. But since I know I'm going to need that, I'm going to just go ahead and sketch the line y equals x. That's y equals x. And then I'm going to try to sketch the graph. I know I'm going to need to sketch the graph y f of x. I'm going to call this one f of x. And then over here, I make a table for f inverse. But let's start looking for the equation of f inverse first. So first, y equals x cubed plus 6. Swap x and y. So x equals y cubed plus 6. We're solving for y, so subtract 6 on both sides. X minus 6 equals y to the third, y cubed. If you take the cube root of both sides, that will cancel the cube for y. Then you get x minus 6 equals y. Then f inverse of x is the cube root of x minus 6. So I need some points to sketch both graphs. So I'm going to start with f of x. I can sketch both of them in my using my calculator, my graphing calculator. Okay, so that is your graphing calculator. You're going to try to find a table that has all the graphs, all the values of or some values that you need in order to sketch your graph. So y equals, clear it. So the function was f of x equals x to the third plus 6. So I'm going to type both the function and the inverse. X to the third. So x, the button xt theta n x raised to the third plus 1 plus 6. Okay. I'm going to type the second one too, which is the cube root of um the cube root of, so it's math and then over left. Well, I think it's just math. So math, yes, over, it's just math. And then go down 4 to 4 and then enter, gives you the square root and the cube root. Then you type the function that was x minus 6. Now I'm going to get a table, second, and graph would give you the table. And then I see some values. The values that I want are the values that I can sketch in my coordinate system here. So all these we cannot use. For the blue is the f of x and the red is the f inverse. So I'm looking for values that I can actually plot in the coordinate system. So I can use for the function f of x, I can take x equals -1, -2, and then y equals -2, x equals -1, y equals 5, x equals 0, y equals 6, x equals 1, y equals 7. And then now let me go to the other graph, see what we can get. I can use -2, -2, -2. But obviously, I can use the same values. Given that the functions are inverse, I can swap x and y. So that's going to be -2, -2, 5, -1, 6, 0, and 7, 1. Just interchange x and y.